Now, what are the steps that can lead to this en echelon joint array and the actual faulting? Well, we could have this bunch of layers here, sedimentary beds, and we have pressure from the east and west due to plate tectonics, and you can see it's starting to kind of kink and bend. As the kinking and bending continues, and we're actually getting real folding going on here, we get some fracturing. Nice little en echelon joints forming. As the bending continues, a large crack can start connecting across those en echelon joints. It's an area of weakness within the rock formation here, and slip happens along that. Therefore, that one is a fault. It's not a joint. So we can see the big dark line here is a fault. There's displacement on either side. Like if we follow this line up, on the other side of the fault, it jumps and is over here before it continues. Beyond the end of the fault is an anticline. It's just folding and bending with some little cracks in it, but the layer is continuous. Below the other end of the fault, again, it's continuous, no displacement. Only displacement is along the fault. If we continue, we may get a flat and ramp type setting like this. You can see that section A is showing a ramp. All of these layers are angled because they rode up this ramp in the fault. And then we get an anticline here because of it bending around. So we can have a fault bend fold on a thrust. You can see, the flat goes up the ramp and then bends over. This is a fault bend fold. A detachment fold is like in here, where this middle area is folding a bunch, but it's detached from this gray layer below it. So it can slide across that, and it can continue to compress and fold, and it's going to therefore lift the layer above it, but below it, hunky-dory, it's nice and stiff and flat and just stays there. We can have folding within a fault zone. So up top is a fault block moving to the right. At the bottom is fault block moving to the left, and between them is an area of sedimentary rock that's softer and it's folding. And then sometimes we can have something called a drape fold. Basically, we had a big fault happening in this crystalline bedrock, probably like some kind of a granite or something. And then the softer, more plastic, more flexible sedimentary layers folded and draped instead of faulting. An old term, not used currently, but still shows up if you're reading older geology papers and books, is something called a fault propagated fold. Or, I'm sorry, drag fold is the old term. Fault propagated fold is the current term. Sorry to create confusion there. Basically, this is the folding happening within that fault zone. So in this example here, you can see from the shape of the folds that something below off the bottom of the screen would have been moving to the left, and the area above this photo off the top of the screen would have been moving to the right, and creating this folding that we can see. Here we can see an aerial photograph of a road that's in dire need of repair. The fault has broken the road as well as the land on either side of the road. This is a surface rupture. The fault made it to the surface. It is not a blind fault. It has surface expression called a surface rupture. This is along a strike-slip fault. You can see that this is a left lateral. If we are standing on this section of road where the mouse pointer is, and we look down the road, it's offset to the left a little bit. If we happen to be on the top right section of the road, looking down towards the bottom left, we still see, hey, when we look across that crack, the road looks like it moved to the left. Now here we have a fault scarp. It looks almost like steps with a little bit of an angle. This is a dip slip normal fault, where basically this surface right here used to be up here in line. That fault block moved down, and then again this. So we have a fault surface here, fault surface here. These are called fault scarps. A lot of times rock continues to erode and fall down a fault scarp because it's an open hillside. Here we have an image of the Mid-Atlantic Ridge. That's where I'm tracing with a mouse arrow here, Mid-Atlantic Ridge. And because the ridge is oriented north-south, we have faults that are oriented east-west. These are transform faults that are running perpendicular to a mid-ocean ridge. This happens because of the curvature of the Earth. We're not dealing in a flat surface, we're dealing with the curved surface over a sphere. So we get transform faults that happen along the mid-ocean ridges. These transform faults are not perfect straight lines. Nobody went out there with a ruler and a razor blade and sliced a gash in the earth to release that stress. It happened at whatever angle and changing angles it could based on the rock properties. So this means that we have areas of transpression along these transform faults. Those transpressional areas, pressure creates uplift, we get ridges. So we have these ridges running perpendicular to the mid-ocean ridge due to transpression on these transform faults. This is very common and very easy to see in many of these ocean floor topography maps that we get from radar and LiDAR. Sag ponds, on the other hand, happen in the transtension areas. We don't get a hole. There's no hole to the center of the Earth at a transtension area. There is, however, sagging and collapse. So as you create that tension and stretching area, the rock collapses downward a bit, not a lot, but a bit, and we get a sag pond because any low area tends to collect water. We can also get fault line scarps that are not in the plane of a fault, so it's different than that other fault scarp where I showed you, that fault block drop down, and then there's erosion and collapse along that fault plane. A fault line scarp is nearby erosion and collapse, not in the fault plane.